Thank you so much, Madam and our Master of Ceremony. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. It's morning time in Maryland, and it is night time here in Malaysia. Esteemed guests, honorable professors, and distinguished participants, it is my pleasure to welcome everyone to our Academy Professor Malaysia APM guest lecture today. We are very pleased to have all of you in this important lecture by our eminent speaker from the University of Maryland, USA, distinguished Professor Dr. Ashwani Gupta. At the Academy of Professor Malaysia, we are committed in making connections with academic experts from various disciplines, from diverse disciplines, as we work together in sharing and imparting the frontiers of knowledge to the academic community as well as to our stakeholders at large. And I'd like to extend our utmost appreciation to distinguished Professor Dr. Swani Gupta for taking his time to be with us in this particular APM guest lecture series. It is morning time in Maryland right now, and I would like to wish formally Professor Gupta a very good Friday morning. As distinguished professor at the University of Maryland, we do not have, I must say that we do not have the slightest doubt about your expertise and contribution in the field of combustion and related technologies. Indeed, it is an honor to have Professor Gupta with us here today. And the title of Professor Gupta lecture is Fuel Flexible High Intensity Colorless Distributed Combustion. Well, it's obvious that it is very technical. Yeah? The title seems very technical. It's all technical jargon, engineering jargon. But I must say, the topic is highly pertinent, highly relevant at a time when the demand for sustainable and flexible energy solution has become increasingly important and urgent. Combustion technology that utilizes various types of fuel with high intensity and lower emission is seen as an innovation that has the potential to transform the global energy landscape, and particularly our local national energy landscape. The Malaysian National Renewable Energy Policy and Action Plan has highlighted the need and rationale for a convergence of various energy, particularly renewable energy, towards achieving a low carbon economy. And furthermore, our Malaysian Renewable Energy Roadmap has aimed to decarbonize the electricity supply sector, particularly via increases in our renewable energy installed capacity from 23% or 8.5 gigawatts in 2020 to 31% or 12.9 gigawatts by 2025, and to 40% or 18 gigawatts by 2035. And such increases in our renewable energy capacity are projected to cut down our carbon emission intensity within the electricity generation sector by some 45% in 2030 and up to 60% in 2035. That's kind of ambitious. The Malaysian government is very committed to expand the renewable energy sector as an alternative source of energy. And as of 2022, is according to our statistic, Malaysia was able to generate some 2% of our electricity from various renewable energy sources. It was just 2% last 2 years, and this shows that we are still very far from our initial target of 20% renewable energy penetration by 2030. We anticipate that Professor Gupta's insights into high intensity fuel flexible combustion technologies will provide pertinent perspectives on improving the efficiency of our Malaysian energy systems. Enhanced performance in combustion process will lead to better utilization of renewable resources, which is very crucial in advancing our energy infrastructure. As a platform for knowledge sharing and academic deliberation, we expect that this lecture will provide new insights, both in terms of theory as well as the practical application of combustion technology in Malaysia. It will be a great opportunity for us to gain a deep understanding on how such technology could contribute to the development of greener and more efficient energy systems in our country, Malaysia. And I would like to take this opportunity to thank everyone involved in organizing this particular guest lecture, particularly our renewable energy cluster, headed by Prof. Dato Ali and his deputy, Prof. Dato Taufik. And nevertheless, my appreciation to our secretariat, our academic professor Malaysia secretariat as well, and also my appreciation goes to the participants. And I would say without the participants, without your presence, this lecture will not be as meaningful or perhaps less cheerful. Again, I'm very hopeful that all of us here will be enlightened, inspired, and we could benefit greatly, God willing, from this exchange of knowledge. Thank you all so much, and I wish all of you a successful and productive session.
Thank you very much, Prof. Jamal, for those insightful remarks. Next, I would like to introduce our moderator for today's sessions, Professor Dr. Taufik Yap Yung Hin, Deputy Chairman of Cluster Renewable Energy at Academy Professor Malaysia. Professor Taufik is a distinguished figure in the fields of renewable energy, and we are fortunate to have him guiding us through today's lecture. Prof. Taufik, are you ready?
Yes.
The floor is yours, Prof.
Thank you, and thank you again, Professor Gupta, to join us, and thank you, Professor Jamal, giving a short welcome note. Well, let me introduce Professor Gupta. Yeah, Professor Gupta obtained his PhD in 1973 from University of Sheffield in UK, then Doctor of Science in 1986 from University of Sheffield, also in UK, and Doctorate Science in 2013 from Southampton Universities in UK. Basically, all education from UK and in UK based. Well, Professor Gupta has been a faculty member in the Mechanical Engineering Department at the University of Maryland, College Park since 1983, following 6 years at MIT as a member of research staff in the Energy Laboratory and also Department of the Chemical Engineering, and 3 years at Sheffield University as an independent research worker and research fellow in the Department of Chemical Engineering and Fuel Technology. He has 45 years of experience, more than 45 years of experience in combustion engineering since his graduation from the Southampton University in 1970. He has authored and co-authored over 850 technical papers, 3 books, 18 edited books, and 22 book chapters. In 2023, Gupta was elected to the Fellowship of the Royal Academy of Engineering, FRN, in UK. In 2020, he was elected to Honorary Fellowship of Royal Aeronautical Society in UK, the highest professional recognition bestowed by the RAES. He is currently Honorary Fellows of the American Society of Mechanical Engineers, ASME, and a Fellow of American Institute of Aeronautic and Astronautic Society of Automotive Engineers, and the American Association for the Advancement of Science, AAAS, and the American Society of Thermal and Fluid Engineers, and the members of European Academy of Science and Art. In 2022, Gupta was included in the top 2% of scientists in the world by Stanford University, which include the researcher who received the most citation across all academic fields. Without further delay, we would like to invite Professor Gupta to present his talk today on fuel flexible, high intensity colorless distributed combustion. The floor is yours, Professor Gupta.
Thank you, Professor Yap, for the very kind introduction. Really appreciate it. And I'd like to thank Professor Jamal, Professor Ali Hassan, and of course the MC, and she did a wonderful job in arranging this. Time difference, I realize, is a big one between Malaysia and here. It's almost 12 hours. Mine is just the start of the day. Yours is winding up the day. Unfortunately, I can't help that because that's the universe which we live in, right? We can't have just one time zone. So I apologize for late start of the day. Hopefully the recorded lecture will be helpful when you get up in the morning or see it tomorrow. You can view it. And if there is any question, you can always send an email to me or Professor Yap. So I'd like to thank Professor Yap to invite me, as well as Professor Jamil to be persistent, send me the title, send me the topic, send me the date, time, and arranging everything. Really appreciate it. Without the great efforts, I think this wouldn't have happened. I've known Professor Yap for many, many years, and he's a great colleague, great supporter, and great insight person in the field of renewable energy. It's a great collaboration. So without further insight in this, I'll start with the fuel flexible, which means that you can have different kind of fuels. If you like high intensity, that means the energy release per unit volume is very, very high. How high? I'll talk about that. So many megawatt per cubic meter. And this here, colorless distributed combustion, is something which I was actually the lead on this, invented this. So the idea is that distributed being that the reaction zone in the normal flame is a very thin reaction zone, at the order of millimeter or even smaller. In our case, we can actually stretch this both axially and radially, so that becomes a uniformly distributed. And that has a lot of implication in different sectors, ranging from commercial engines to spacecraft application. And you'll see the value of this ranging from a microcombustor, which you can use in small portable power production, to high intensity like the gas turbine power generation, and as well as the electricity generation used for different purposes there. So before I start this, I thought it'll be a good idea to give you a bird's eye view, since you can't see our campus here. So that's our campus. On the bottom left-hand corner is a small building. So this is where exactly the University of Maryland started back in 1856. That was the students will take the classes downstairs and sleep upstairs, and this extension was made after this. So, and that's the bird's eye view of top left-hand picture of the Glenn Martin Institute of Technology. Glenn Martin was the one individual who was actually very pioneer in the aerospace application. And the pillars here, you see the cherry blossom that was given to the USA almost 100 years ago by the president of Japan, and is actually given some award this year because some so I'm in the James Clark School of Engineering, and the name was changed back in 86, 87 timeframe. where it was College of Engineering, and now we call it James Clark Foundation actually endowed this whole position here. And the department which we have is the Aerospace Engineering, and I'm a affiliated faculty member professor in the Aerospace Engineering too. Bioengineering, chemical, civil, environmental, electrical, computer science, fire protection, which is #1 in the whole country, as well as the material science and engineering, which is top 18 school in the, and the we are a public institution, which means that funds are received from the state of Maryland, and in terms of the public school, we are in the top 12. I think recently I was told that it's top #8, and this is in mechanical engineering in the USA, and they'll talk a little bit more about what that is. In terms of James Clark School of Engineering, there's about 200 faculty, having a total undergraduate population of about 38,000 graduate, this number here. And you can see the annual engineering degrees, which we award students about 900, MS about 450, and about 150 PhD students. And our research budget is $201 million per year. This is for the School of Engineering. As I mentioned, that we ranked number 12 and both the undergraduate and graduate. And of course, if you look at the public school, we are number 9 in the undergraduate ranking in the US. So it's pretty high. So when I compare number 12 and the undergraduate graduates, I'm comparing with MIT, Princeton, Stanford, Harvard, and so on. And incidentally, we are ahead of Harvard, our ranking in the engineering area. So more of the department, this is where I am. And this is the statistic, the latest one. We have fairly large size faculty, 46 tenure track and tenured faculty. And if you look at the number of society fellows, it's about 75. I think this number may be a little underrepresented. It's close to about 80 right now. And National Academy of members, that's the highest thing one can bestow to engineer, National Academy of Engineering. And I'm not including the Royal Academy of Engineering, to which I'm a fellow, is 8. And the book editors, 11 archival publication. We typically publish about 150 to 175 publications for a faculty of 46, which means that we are publishing about 4 papers, journal papers per year, and more than that in the conference presentation. Our research funding for the Department of Mechanical Engineering is about $21 million. And this is the population for the undergraduate and graduate students, and of course the visiting faculty, visiting scholars, and how many degrees we award in the mechanical engineering bachelor's, MS, and PhD. So you can see a large number, 35 to 40 PhDs awarded per year. So going to the issue of energy, energy is not an issue for only Malaysia, it's a worldwide issue. So going back millions of years ago, you can see the distribution million years ago, for example, how much was the energy consumption, how many kilowatt hour per person per day. You can see that the energy usage back in the old time was all about the food. So food was the main issue, and the energy use was only for the food purposes. And as the time progresses, 100,000 years ago, you can see that the food was one, but then came the added part, which is the household. So household and the food became equally distributed. 7,000 years ago, we added a little more, which is involving the industry. So industry sector, which was an important one, and that took more energy. So closely looking at these numbers here, bars, and you can see the energy used is actually growing from a million years ago to 100,000 years ago to 7,000 years ago. And even as late as 1,400 years ago, the energy is still growing. And 1900, you can see that the other issue which come up, the industry. So this industry part is the traffic issue, which means the mobility became an important one. as we look at the 1900s. So start of the automobile was around the turn of the century, 1900. So you can see the energy became much more important here. So 1990, and that's the latest which is available. So you can see everything seems to grow, and not only for the food area, but also the household industry and the traffic continues to grow, starting with only about few kilowatt hours per day to almost 140, 150 kilowatt hours per day. Yeah. So it's growing, which means that we need to, and of course, and we need to meet the demand in the various sectors. We can't switch just one sector here to the next sector here. So we need to satisfy. So look at the population, that gives you a bird's eye view, the world population growth in the history. So several million years ago, which are the old Stone Age, you can see the population were very, very small, only about 2 to 5 million. And the New Stone Age commenced, which is about 10,000 years BC, before Christ. And you can see the steady increase in the population of 2 to 5 million to about 7,000. And as the time progresses, the New Stone Age, and Iron Age, Bronze Age, Iron Age, the Middle Age, and the Modern Age to where we are. And you can see very sharp increase as we go to 80, 1,000, and almost 2,000. You can see the population growing to over 8 billion people on this planet here. So the population on this planet is really growing very, very rapidly as the time has progressed. So here's the close view of what the number of population, where we are and where we're going. Roughly about 7-8 billion right now. And if they keep the scenario, the economical issue the same way as we see it, we can see the high trend of about going to about 16 billion. And on the other hand, the low part, maybe about 6 billion, and somewhere which the medium path is about 10 billion. So given that the May and the recent trend is the population still continue to grow, and we expect this to grow all the way to about 10 billion by the end of this century, which is about 2100. So population is growing, the energy usage is growing, which means that we need to bring the energy, and this is where contribution from various researchers, including Professor Yap in Malaysia, is very, very helpful in satisfying the need of the society and the human being to making the life comfortable. So if you look at right now, there is about 3 billion people have either no electricity or very limited access to electricity. Electricity, I believe, and I really believe that, is a very integral part of the society where we need to have the availability of electricity to everybody. If going to countries like Africa, only thing they wish is that I had the electricity, I could turn it on, cook the food, had the comfortable life. It will change their life dramatically to what they encounter right now. So world population currently, we need to design food and food supply for about 8 billion people. And over the next 50 years, we expect this, as I showed in the previous graph, to roughly about 10.5 billion people worldwide. So, and if you look at the distribution between where we were in 1800 to where we're going to 2100, you can see the developed countries and the increase in population is relatively small. There is a small finite increase, but the developing countries, this is where the major growth will be. And remember that the point I made about the electricity demand in the Africa and some of the developing countries, this is where the big wish, big need is for providing electricity for everybody. So, so that means the availability of the energy as well as the electricity is not uniform to where we need to see over here. So if you look at the Industrial Revolution, which is going back in the old time, was the horse was our major carrier, and this is not too long ago. It's just even 1800, you could see the horse buggies going from transport from A to B. where I am at the University of Maryland, I show the campus where it was. In fact, back in the old time, people used to travel from Baltimore, which is about 25 miles north of College Park, where I am, and they'll go to Washington, which is only about 10 miles from College Park. So this was almost a midpoint, not quite, but almost a midpoint. So stop overnight and park the horses near to the building and rest, and then continue the next day. And if somebody is brave, they will continue the journey the same way. So horsepower was the one which is horse is the one which is putting the buggy. So those who are not familiar with the horsepower, you can think of the manpower, 13 very strong men, that's equal to 1 horsepower. So that kind of gives you how much horsepower we're talking about. So horsepower to horsepower is really what we're talking about. So automobile engine, which we're all familiar with, you can see the automobile over here. I put one of the General Motors cars here, about 300 horsepower. You might say, well, my car is only 200 horsepower or 100 horsepower, but it's not the point. I think 1 horse going to about 200 or 300 horsepower. So you can see the order of magnitude or 2 orders of magnitude increases, which you see it here. And if you look at the train from 300, you're talking about 10,000 horsepower. So much larger increase in the power, which you see it here. On the other hand, if you look at the aircraft, and this is the 787, is 100,000 horsepower. So very, very large increase. In other words, the power which you saw back in the old time, horse and buggies over here, you can see that how much is increased from 1 to almost 100,000 numbers over here. And in terms of electricity need, you can see the map over here, and I can share some of the map with how the light is lit up in the rest of the world here. And I'm basically right over here on this corner here. Let me see if I can put the laser pointer here. So I'm right over here, and this, the eastern part is pretty much lit up on the western coast here. California, you can see some dots, which is Los Angeles here, San Francisco area, and the Las Vegas is just right next to the Los Angeles, which you see it. In other words, the point of the message here is that it's not uniform, and the northern part here, you see the Canada a little bit lit up. So now we come to the feature presentation, which is the high intensity colorless distributed combustion fuel flexibility is something which we need to talk about. So I was one of the lead in developing this so-called the high-tech technology. And if you look at the how this evolved in the former time, and the idea was to make it a bigger and bigger power station. So we have a 50 megawatt power station or 10 megawatt power station. That was the key thing. And the goal there was to how do we actually develop it, and how do we actually produce the energy from here, and how do we produce the electricity. So the electricity production efficiency. And so back then, there's your combustion chamber on the left-hand side, and the tail end, you can see some of the pollutants. And this is not too long ago, only about 70 years or 75 years ago. You can see large pollutant which are coming out the tail end. So the bird's eye view of the combustor is given in this box here, which is the industrial furnace, heat exchanger, and then the power generation unit. And the tail end, we basically throw the pollutants in the environment, which consist of not the particulate matter, but also all the pollutants, including the CO2, which considered now as the pollutant 2, which back then we did not. So came the 1960s, 10 years later, a decade later, and you can see the what has changed here is making it bigger. So 50s or 60s, the idea was to make it bigger. How big? We want to go from 50 megawatt to about 200 megawatt or 250 megawatt. So we made it bigger, and came the 70s. In other words, rather than a yellow flame, which is a sooty flame, more emission, so it became the concern that how do we keep the environment clean, because the environment was a big issue. And this is when the EPA was formed around 1970 timeframe. So you can see the color of the flame here is it's reddish and yellowish in color, and the idea was to cut down the pollution. And you can see the blue color flame, which is over here. Blue is more favorable compared to the particulate emission, which you're seeing it here. And the other part, which you see, the stack signature, which is on the left-hand side is pretty large, and the right-hand side is pretty small. So which means that I reduce the amount of pollutants which are coming in. And the bottom here is something which you collected in the bottom part here. So in 2 decades, we made a tremendous progress in 2 areas. Number one, making it larger, and number two, cut down the pollution, not completely eliminated, but as significant reduction, which you see it here. And this is the time frame which I came in, so-called the high tech. And I was actually the one originator of giving this name called high temperature combustion. And the high tech sounded good because it's high technology, and this was more for the industrial furnaces. In other words, how do we utilize the energy in industrial furnaces, which is environmental benign, as well as the cut down the emissions, which we see it here. And on the right-hand side is one of the pictures which you take out of our lab, and you can see it's not just the bluish color, but it's tinted a little bit greenish color here. So those in the spectral area, what this means is the blue is about 480, 490 nanometers, and greenish mean that is somewhere around um, green color, which is around 515, 520 nanometers scale. In other words, the emission is changed from low wavelength to a little high wavelength, which you see it here. So this was the major revolution thing, which you see it here, and inside you can see the greenish tint over here. So the idea was that we want to cut down the emission, and here's the industrial furnaces. We denox the NOx emission reduce, and we cut down the emission of the SOx, and so on. And the idea is we get basically no emission, or very limited, very, very close to zero emission, which you see it here. And 2000 came, and this is where the colorless combustion came in. And that was some of the work which we did at the University of Maryland. And that was really the evolution of the colorless flame here. And you can see inside here in this box here, physically, you basically see a black box here, no flame, you can visualize it. On the other hand, when we put our laser diagnostics, you can now see the inside, and this is the flame which is evolved over here. And this was so-called the particle image velocity diagnostic, which we utilized to capture the flame here. So these are the velocity vectors you see. So here you don't see the flame, but we illuminate it with the laser diagnostic, you can see the inside the flame. But physically looking at it, even using some illuminated light factors here, and the box here, you don't see any flame at all. So I named this the colors of combustion, and that was the one which is a revolutionary thing back in the 2000. And now you can see the usage, and not only in the US, UK, even some of the Asian countries, they use that in addition to Japan and China. So this high-tech technology disseminated very, very rapidly, including countries in Europe like Germany, France, Sweden, and even countries like Poland is heavily used here. And I'm happy to see that in countries like India are using also the high tech for energy saving as well as the pollution reduction. Came the time frame of 2010, 2020, this year too become an important issue. So same power plant, we basically take out the DNOx, we take out the NOx emission, particulate emission, and the leftover is only CO2. So we separate out the CO2 to sequester it. So you have a basically exhaust gas, which is only giving H2O, which is the water vapor. Water vapor is also a greenhouse gas, but there's nothing much we can do because water, we need it, and that's needed for the. So these gas turbine with the CDC, colorless distribution combustion, is really where our focus has been over the last few years after developing the industrial furnaces, which is happy to see that's used in many, many countries worldwide. and some of the countries actually has used it and made a multi-billion-dollar business in this domain here. So what are the benefits of the high-tech technology which I'm talking about? Some people call it flameless oxidation. Germans, they call it flameless flux burners. And I stick to our definition of colorless because flameless, it's cannot be because if you don't have a flame, that means you have no heat and no light. Colorless is more suitable because it's no color, but at the same time you have a flame, which is distributed in the sense that it's uniformly distributed all over the combustion. And one guy from Italy, I told him he was actually working in the area of soot particle diagnostics, and he came up with the idea of using mild combustion, which I don't support the name because it's not a moderate intense. It's basically distributed combustion, which you see it. But given that as a may, you can see that how the Germans, the US, and the UK, and many other countries have used it, including far east, like Thailand and other countries too. So the technology actually provided significant energy benefits of energy saving in industrial furnaces. Our goal was to have a energy saving about 30%, and I'll show you how much we were able to achieve, as well as the CO2 reduction. And CO2 reduction comes from because we have less energy which is utilized in the furnace to do the same job. So therefore, the CO2 reduction is there. And actually, if you give the overall numbers, it's a tremendous amount of CO2 reduction, which is achieved there. Pollution reduction is about 50%. In some cases, we don't even need the post-capture devices to reduce the pollution. And because it's distributed all in the combustor volume, you can actually reduce the size of the overall furnace to roughly about 25%. Or if you want to use the same furnace size, you can boost the capacity to produce more goods from the same furnace by roughly about 25%. And uniform thermal field distribution in the entire combustion zone. And I'll show you the actual results over here, hopefully all of the time. But basically, the entire combustion zone, you can have a temperature which is within about 30 degrees K. And this is unheard of because the private data or any combustion book, which you look at it, the flame goes from the normal room temperature all the way to about 2000 degrees K. So you can see the difference in temperature, about 2000 degrees K. And here we are talking about the entire combustion zone from the start of the burner to the end within 30 degrees K. No low noise, we've shown it almost 7 dB noise reduction. In fact, in some cases, you can't even tell whether the flame is there or not there. So that's very favorable too. Very high heat flux, those in the computer modeling, they'll see it, the typical value, the heat flux they use is about 100, 120 kilowatt per square meter. And here we had the measured value as much as 3 times as much. So high intensity CDC, which is more megawatt per cubic meter. And that's really where our gas turbine combustion becomes very, very useful. So we transitioned from industrial furnaces to gas turbine combustion. And we also looked at some of the waste, how do we convert the waste into useful hydrogen-rich syngas. And you can see that we've been using this high tech to convert the waste into hydrogen-rich syngas. And hydrogen is a premium fuel, so we can clean it up to get a fuel, hydrogen fuel, and I call that a fuel reforming, because you take any hydrocarbon material and you actually convert it to hydrogen fuel itself. So potentially it's usable for different kind of fuels, and I'll show you some of the data which is used with a different kind of fuel. So very, very attractive proposition to what we see it here. So in principle, the schematic is given over here. Here's the box with the high tech is used. Here's an example of the steel, and the idea here is you want to heat up the steel to do the job. So the high-tech flame is introduced over here, and essentially you take rather than the exhaust gases to be wasted, we recover the heat from here and we feed it back into the upstream section, mix it with the fuel. So in other words, we have both the heat recirculation, which is this guy here in the bottom part, and the gas recirculation right over here. So prepare the mixture before the ignition takes place. So that's really the key in which we are utilizing and the high tech here. So this is more of the detail, the concept, how it's used as over here. So the industrial furnaces, typical application is about less than a megawatt per cubic meter atmosphere. And the reason I bring the atmosphere is because that gives the applicability in all kind of application, power application as the propulsion application. So furnace application, the typical megawatt may be about of the order of about 0.1, 0.2 megawatt per cubic meter. On the high end, maybe 0.5 megawatt per cubic meter. On the other hand, if you look at the power generation using gas turbine, it could be anywhere to 10 to 15 megawatt per cubic meter atmosphere. In other words, the denominator atmosphere takes care of the whole thing. And it's not my part. In fact, this is something which, in looking at the literature, back in the 1950s, that was proven that if you take the atmosphere, that actually correlates very well. So what that means is that you can take the atmospheric pressure data and correlate it to the high pressure environment, which you do it over here. So these are the schematic, how this whole thing occurs, how this takes place. And essentially take the exhaust gases, recirculate it, bring it back again. And this is the schematic which you gave in our book, which was published. It's called the High Temperature Combustion Film Energy Saving to Pollution Reduction by the CRC Press. And in fact, the book was sold out within 6 weeks of the initial publication. Then we had the second publication that was sold out pretty quick, and the third edition, third publication. So as I mentioned, that some people call it flameless oxidation, flux, Germans, moderate and intense low oxygen dilution, and mild combustion. Name is attractive, but it's a misleading definition. So I would not use the mild because it's not mild. There's no boundaries to what we're talking here. So how did we develop this high-tech technology? And the normal combustion is basically use the normal air. And here I show on the left-hand side of this picture here, the conventional flame, which the oxygen concentration in the air is about 21%. So you can see the envelope of the flame where the flame is stable. So if you dilute it in the normal flame, basically the flame on the right-hand side extinguishes. And if you preheat the temperature, you can see that the envelope on the right-hand side expands. So the high tech is really somewhere in this vicinity here. And of course, you can go down to as low as a few percent oxygen concentration. What that means is that you're able to get even the exhaust gases of an industrial furnace to recirculate it back, and you can still have a flame. It may not be visible, but you can still have a flame which is heat releasing. Or on the other hand, looking at the syngas, synthetic gas of very low BTU gas, you can actually burn this in the high-tech furnace and still give you the heat release. So it becomes an open, wide area. And how do we do this? Basically, gas recirculation and heat recirculation, which I showed in the initial picture, and this over here, heat recirculation, gas recirculation, to come to this part here. So on the right-hand side and the middle picture here is basically what you see, the flame pictures. And in the normal flame, you can see the hybrid color and blue flame in the right at the near to the burner exit, followed by a yellowish color flame. And as you increase the flame air preheat temperature, you can see the feature remain the same, but the yellowish color actually enlarges as you heat the air preheat to much higher temperature. So for example, 1000 degrees C air temperature, you can see more yellowish part. as opposed to bluish far. As you gas recirculation, which means that more the oxygen concentration is reduction, and you can see the flame volume on the right hand side to expand, and in some cases you have almost a bluish color flame or turning to go to the green, and but the flame volume nevertheless increasing compared to what you see in the part here. And here's the part which I'm showing it here, transitioning from bluish to bluish green here. So this is the one which actually people in the community, they call me as Mr. Green Flame. So if you hear the green flame, that actually originated from the University of Maryland, and that's where the name comes from. So it's so much higher temperature and reducing the oxygen concentration. And on the right-hand side, you see the schematic of what happened in the normal flame here. So inlet temperature Tn, adiabatic temperature, that's what the flame is going to provide you, very high peak. And as you proceed in the combustion process, move in the direction, so you had the exit temperature. So this is the region where the NOx is formed, because the NOx is formed at higher temperature and the oxygen availability. So it's fixation of the atmospheric nitrogen gives it. So, and as you preheat the air, it's in the normal circumstances, this peak will rise. That will basically generate more and more NOx. So this is where this technology actually back from England, which were using basically to preheat the air, and where they failed was not recognizing that I'm actually producing more NOx because of the higher temperature which I'm seeing it. On the other hand, we got the regeneration and a very high temperature, dilute the gases to get the high-tech region on the right-hand side. So these are the detailed features which you see it here. And color, it's the combustion, or also the green combustion, is basically a very novel technology that provides significantly lower pollution. And I'll show how low is low. That includes the NOx emission, the CO emission, as well as no emission of particulates, no soot emission, no carbon emission, as well as the hydrocarbon emission. And of course, the flame thermal uniformity is very much uniform in the case of distributed combustion. Because of the energy saving, I'm putting less fuel in. I'm also getting the CO2 reduction in this case over here. Distributed combustion is featured by controlled mixing of the reactants. And this is where I'm talking about where, and it could have the steam, which is the CO2, inlet steam, nitrogen, or even steam to reduce the emission. So fuel flexibility, that means that I can use different kind of fuels. Irrespective of fuel property, I'm still see the same thing in this case here. So here I give the basically in terms of academic exercise, in terms of looking at the turbulence as well as the scale, length scale, which you see it here, relative to the laminar flame thickness, and the wrinkled flame length zone is over here, thickened reaction zone over here, and basically the distributed combustion is somewhere in this vicinity here, where the Damkohler number is less than 1. On the reciprocal of the Damkohler number, which is the Colorless number, is somewhere in that vicinity. So thickened reaction zone is somewhere in that vicinity here. So the normal spot, which you see it here, very low Colorless number of the order of 1, which is more true for the IC engine. You can see the onset or the hotspot zone, and that's the one which is giving you high emission and also unstable combustion. So basically, you see the global feature, and of course, in this region here, the laminar flame. So this was the invention which we made in conjunction with some of the Japanese authors, and also at the time, the International Flame Research Foundation were involved, and that started in 1946, somewhere there, that time frame. And when they saw where we are going to, they actually changed their whole mission, going from what they were looking at to our side, looking at the colorless combustion, how can we utilize it? And now they're happy to utilize what we started off with. So that was a major achievement, the International Flame Research Foundation, making a major diversion from where they were to where we're going in this direction here. So basically, that's the direction which we're going into thickened flame, and as opposed to the normal flame which we're going here. So having said this, if you look at the distributed combustion, it's basically based on the high-tech technology, which is a high-temperature air combustion technology, and the regime is controlled by the fast mixing or the hotly circulated reactor products and spontaneous ignition to a blend and distributed zone, which gives you very low NOx. And I'll talk about how low is low, and avoid the hotspot zone because everything is distributed here. So if you look at the damp Kohler number, as I mentioned, the damp Kohler number in the previous case is about 1, or the inverse of the damp Kohler number, which is the Colorless number, is very high. And so you can see the damp Kohler number is about 1, and this is where the high-tech distribution regime. On the other hand, the colorless distribution combustion, which is more for the gas turbine application, the Reynolds number is pretty high. So that's where the CDC sits it. So CDC is not the same as the high-tech, and high-tech is not the same as CDC, but there are certain differences. But the common feature is still we don't see the flame. And on the left-hand side is what physically you see it in the normal flame. This is the looking at the cross-sectional view of a combustor, and you can see the basically tinted blue zone over here. So that's the diffusion zone which you see it. So when I introduce this in a colorless distribution mode, you can see the whole flame color is disappeared. And you might say, well, there's the yellowish background, orange background. It's actually the background from the coating which we have on the material that's glowing. But otherwise, there's no visible flame, which you see it here. So it's so the challenges which you see it here, and when you go to the high tech, is the low residence time at the high velocity, because the velocities are pretty high, and that means that we need to control the flame in a small volume. And I'll talk about the small volume and how that is. And recirculation is important, and mixing of these gases with the fresh reactants, that's very important. And if you don't do this, that means that we're going to impact the flame stabilization. So it's all about knowing how do we prepare the mixture. If you don't prepare the mixture, especially in this and in the high intensity application, that becomes a very, very challenging task in this application. So we started this work in our lab to look at what the CDC looks like. And so our quest was to look at the colorless distributed combustion, and the University of Maryland near zero emission fuel flexible, which means that I've used it for different kind of fuel, and I still don't see any emission using CDC in this example here. So you see the whole range of combustors here, and the common feature is that we had the facility in which I can reduce the reactants on the upstream or from the downstream, and the exhaust gases are exiting over here. And there's the another flame here, which is preparation is upstream, and the same marker here, much reduced in size, and you see the exit port, thermocouple port, and the idea was to be able to measure it, and that's more of a circular cylinder. That's the picture which I showed you, and this is the one which is very, very high intensity on the right-hand side here. In other words, you can see these size dimensions here going from this volume here to about this size here. So going the right direction to have a high intensity and very uniform, and the oxide gases here exhausted away. So basically, gas turbine is the one which is what we're using for the CDC, and the goal is to reduce the emission, and what strategy we can use, and what are the important factors for the CDC design, and look at the literature, what people have done. And I'll show you some of the sample results. which is obtained at some of the earlier work, which is 0.1 megawatt per cubic meter atmosphere, going to low thermal intensity. In other words, moving in the direction of gas turbine, which are high intensity, 5 megawatt, 28 megawatt, 85 megawatt, and then going to all the way to 200 megawatt per cubic meter atmosphere. As I mentioned, that modern gas turbine application, which is used for the power application, at the present time, only limited to about 15 megawatt per cubic meter. So you can see that I am an order of magnitude larger than what is used in the current practice of electricity generation. And you might say, well, how does it compare with the aircraft? You can see the aircraft these days, they can go all the way to about 50 megawatt per cubic meter atmosphere. So even compared to the modern aircraft, I'm about 3 times, 4 times high compared to what they have over here. Emissions, reaction zone, dynamic pressure, flow field characteristic, and of course, where's the CDC heading to is where we really are going in this model here. Little background on the gas turbine combustor design. The gas turbine design consideration, basically we require low emission, very high thermal intensity. As I mentioned, for the stationary power application is 15 to 20 megawatt, and the residence time is 20 milliseconds. So that's a very, very important factor which you see it. And the reference velocity for those who are working in that area is typically about 60, 70 meters per second. We need very stable combustion. And then, of course, the noise levels below combustion instability. That's the important part here, because that's the one which is gives rise to oscillation, pressure oscillation. Low pressure drop, typically less than about 5%, and wide stability limits, turn down ratio 5:1 because low power, high power. And the pattern factor, which is how uniform it is an important one for the gas turbine application. So what you see on the lower left-hand corner is how the emissions are. If you look at the lean combustion, you can see in the fuel lean case, you had the emission of CO to go high. And as you go to the richer part, emissions are very low. In other words, near to the stoichiometric, you see emission of hydrocarbon very low, and is go. And so low emission. On the other hand, the NOx emission is as you increase the fuel, and the NOx emission basically increase. So the narrow window where you have the low NOx is this small window, which is really applicable. So land-based combustion turbine, as I mentioned, it's about 15 megawatt per atmosphere, 16 atmosphere they use, and the length and the overall equivalence ratio, the global equivalence ratio, 0.35 to 0.4. So that's where the land-based and the aircraft turbine, you can see on the right-hand side what we get it here. So in the aircraft, the inlet turbine combustor temperature is about 700 degrees K, and the takeoff could be even higher, as much as 900 degrees K. And the hot gases which are coming into the turbine could be about 1500 degrees K, and that's going to the so-called the TIT turbine inlet temperature. So these are the challenges which you see it here. So that not just to burn the fuel and get it output, but we need to pay attention to the high intensity, stable combustion, low pressure drop. And in the actual schematic is given over here as fresh air comes in the combustor into the compressor, and that goes to the combustor, and to the turbine, that's the output. So it's the open-ended in this part here for both for the aircraft as well as the stationary gas turbine. So what did we do here? We bring the whole thing to the lab and see what I can do in terms of determining what the factors are where we are seeing it. How am I doing with the time? Time is okay?
Yes,
Time
Prof.
wise? Yeah,
Yes.
okay. So so the important part is to look at what the gas circulation is, how much the fuel dilution is, fuel oxidizer is. So I get the acronyms here, which are the mixing air into the part here, or in the oxidizer on the product gases, which is the burn gases, how much they are entrained over here. And you can see the diluted fuel and oxidant dilution. In other words, that's going to control the mixing and the ignition delay in the overall factor here. So here I take the example of the air going in here, very high velocity jet, and the burn gases with the fuel is going to entrain in this jet here. So basically, that's going to dilute this part here, and both on the left side and the right side, and the excess gases are exiting over here. On the other hand, if you take the air and introduce a small amount of fuel here, so now we had the burn gases which are introduced over here, mixing with the air, and then the fuel is also getting diluted, and the both of them together over here mixing, because remember the amount of air is roughly about 10 times more than what you see with the fuel, assuming that the methane is the fuel. So we have the overall mixture proceeding over here. So very high velocity jet, which consists of entraining on both sides of the burn gases as well as the fuel stream coming in. So the mixture is the one, and that has to be, mixing time has to be less than the ignition time for the mixture here. So I'm going to dwell on this part here to see what the schematic would be needed and who's done what to be able to achieve the condition which you're doing it here, and because there's no simple relationship. So here's the same schematic, which you see it here. So the air introduced here, burn gases going over here. So now I can take this fuel, either introduce upstream or fuel is imposed in the opposite direction, and the burn gases. So in this case, the air is here and the fuel is here. So the fuel is opposite. So FO, fuel is opposite. And in this example here, fuel and air in the same direction. So F as fuel, which is the fuel on the same side of this combustor here. And in this example here, the fuel and air are pre-mixed. And what happened if I pre-mix the fuel and air and then introduce the burn gases to be introduced here? On the other hand, I can take the air on the opposite side and inject it with a very high velocity and let the gas entrain in this part here. So now I can subdivide this, the air coming in from this part here, and fuel on the opposite side. So the fuel will be entrained after getting entrained from the from this section here to mix with what I want to achieve over here. On the other hand, I can introduce the fuel somewhere in the middle in recirculated products with the center part here. So I call this RC, and this is the opposite, reverse opposite, reverse central, and reverse same side over here. Or I can have the reverse in the premix case over here. In other words, the fuel and air premix and go in the loop. And so I had the different schematic, which I can get the opposite picture here. So essentially, the idea was to matrix, let me look at it and see which one is giving the low emission, because that's really our goal. And these are the factors which we need to obtain in designing this whole thing. So here's the results, which you see it here for the furnace application. And this I'm giving it in thermal intensity. Thermal intensity, as I mentioned, is typically about 0.01, 0.05, or 0.1, 0.5. So anything less than 1 megawatt is furnace application. Anything about 10 megawatt is for the gas turbine application. So you can see the whole range of work which is done, including Roman Weber from International Flame Research Foundation, some of the other work, as well as my own work done back in year 2000, early 2000, and so on. And you can see the industrial application was the one which we were doing it in conjunction with the Japanese. In fact, I was the international consultant to the Japanese project for almost a decade. And this is where all the work evolved here for the furnace application. And you can see how much the thermal intensity was and who was looking at this, because that was a dynamic activity back then. And And these are the corresponding geometries, which you see it labeled over here, who did what, and what kind of configuration which we did, including the work from Georgia Tech, Baba, and other work which you did, and was central, how much was done. So ultra high thermal intensity combustor will lead to very compact combustor. This is what our goal was, to look at the overall configuration. So here's the example of what people did and how much the NOx they were obtained. So on the left-hand side, you can see where the fuel from the same side of fuel from the opposite side, air from the opposite side. So here the fuel, here the air, same side. And here is the fuel and air from the same side, but it's the reverse direction. In other words, that's the direction which is going in. So here is the air and fuel from the same side, and here the air and fuel, but they are rather separated. So the separation distance is actually very, very important. And this is what led to, when we probed into a little more in the detail, that the Thring-Newby parameter became very, very important to consider this. And we didn't realize that this was important and how much distance we need to keep. But the bottom line is that the studies which you see it, much of the studies were the atmospheric pressure, because that was our goal, and to apply it for the furnace application. And you can see the heat load was only about 500 kilowatt, or 20 kilowatt in our case, and or 50 kilowatt in our case. And some of the other studies which you did in conjunction with the Japanese, and you can see they're going to 350, and how much of the NOx emission which you're seeing it. So in one case, you're seeing 9 ppm at stoichiometric equivalence ratio, and CO only about 1 ppm or less. On the other hand, if you look at some of the high-tech work which we did, you can see that emission changes from 9 to 1 to 44 to 9 ppm, 8 ppm, 12 ppm. In other words, very, very low NOx. And incidentally, 10 ppm, you might think it's a high number compared to what other people have got. In fact, we got even smaller than this, but that's just the in other words, what it reveals is that the geometry, configuration, how you introduce the fuel and air are important bearings on what the NOx emission you're going to see it. So you can have anywhere from 1 to 10 ppm of CO level in different configuration. There's more of the similar kind of data with the other investigators all around the world, which they did. And you can see much of the data is atmospheric pressure and the air velocity going from 20 meter all the way to 100 meter per second. And the fuel is atmospheric temperature, air is atmospheric temperature. And the NOx level, you can see the equivalence ratio, even at stoichiometric mixture or near to stoichiometric, you begin to see you can achieve 1 or 2 ppm. And CO level 10 to 20 ppm. That was a very, very high achievement, which was never demonstrated before in the history of burning of the fuel, which you see it here. More of the same thing, where do we go? And so different range of heat load, 200 kilowatt, to very small one, which is the 3 kilowatt, and to several megawatt, which you see it here. Again, NOx level going from 10 ppm, 1 ppm, in some cases even a fraction of a ppm, and CO level, some cases going to 10,000 ppm, 5,000 ppm, in other cases going as low as 10 ppm. In other words, the geometry impacted much of what we see in the practical application. So that was an important role, and everybody was getting very, very excited. And at the top, you see the thermal intensity, all within the vicinity of 0.8 to 5 or 10 megawatts. So this is probably the closest which you see it in the high intensity combustor, 10 megawatt, 15 megawatt. So you can see the NOx level going from 10 to 15 ppm, and the CO level as low as 9 ppm, and the other cases about 5,000 ppm. So that was an important challenge which you see it had some of the Georgia Tech work you can see they achieved the NOx level to 1 ppm and CO to 1000 ppm. And the combustor was very simple. And so this actually configured to what we were doing it here to prepare the mixture in a very nice way to be able to condition before the ignition takes place. So that's the one which actually gives the very favorable condition to where we need to go. Some more geometries which you see it here, practical application, again, reaching the condition that you can get the NOx level anywhere from 1 or 2 ppm going all the way to 30, 40 ppm, and the NOx level, CO level. So it was a major, major achievement. NETL, National Engineering Technology Laboratory in the US, they did this, and they were actually able to show that you can actually get sub-unity ppm NOx level. AFRL, which is the again the US, and Technion and the NETL in the US, which was more of the rich quick burn, lean burn, and trap vortex combustor. They thought that was a good way to path forward to reduce the NOx level, but you can see the NOx level were pretty high, 40 ppm, and CO levels were still 10 ppm. So that was the dynamics of where we go, and this is summary of what you're seeing at the different configuration, and we summarize this thing in a nice way, which is forward same side, forward in the opposite direction, fuel and air. In the premix case, what you get it. And so we did some of the CFD simulation, what exactly it looks like. Unfortunately, I don't have the time to show all the data, but nevertheless, we configured something which is can go from low intensity to moderate intensity to very, very high intensity, 20 to 40 megawatt per cubic meter. And you can see the NOx level going from 4 ppm going down to about 1 ppm at equivalence ratio of 0.5. You might say, well, what does that represent to 4 ppm or 5 ppm? This actually very comparable at the equivalence ratio of 0.5. Remember, I said that the gas turbine combustor in the stationary power application and typical overall equivalence ratio is about 0.35 at the normal setting, which you see it. So even richer than what normally used, you were able to see the NOx level to about 4 or 1 ppm level. So that was actually very, and these are different kind of fuels. I didn't go into what kind of fuel you're using it. And we've been using it, methane, propane, and some of the syngas, which you're producing here. So this is basically a summary of our summary, University of Maryland summary, and some of the sample results, which you see it here. And we did all the way from 5 megawatt per cubic meter atmosphere all the way to about 200 megawatt per cubic meter atmosphere. And you can see our thermal intensity results to how much the emission, which you see it here. So you can see the NOx emission in some cases as much as 10 to 12 ppm. On the other cases, we are seeing the NOx level only single digits, 1, 2, or 3 ppm. And its configuration gives you what is low and what is high. On the other hand, the CO emission, you can see that in most cases, it's about 10, 20 ppm, and some cases as low as 4, 5 ppm. So this was a major, major discovery in terms of how do we actually reduce the emissions. And of course, the soot and carbon, they didn't exist, and the hydrocarbon didn't exist in any of the feature which we're presenting it over here. So so I'll go to some of the more detailed effect, what you see it, effect of air and fuel injection, what the diameter we need to have. So that gives the way and means how do we inject it. And you can see in equivalence ratio as much as 0.9, essentially stoichiometric condition, having a NOx level at 15% of O2 to about 6, 7 ppm. That was a major, major achievement. And you can actually even reduce it even at 0.9 equivalence ratio, near stoichiometric, and NOx level as much as low as 5 or 6 ppm. And same thing with the CO at equivalence ratio 0.7, which is not quite what you needed in the gas turbine combustor, but people wish they could go to as high as 0.7. And the reason why they don't go to 0.7, 0.6 is because the NOx levels, CO levels are pretty high. In our case, we are actually reducing it much lower level here. So these are some of the features which you see at here. We even examined some of the pilot flame having a thermal intensity of 6 kilowatt and thermal intensity 200 megawatt. And that's the combustor, which I showed it earlier to visualize what we're really getting at. So we examined this using the PIV, particle image velocimetry, and to see how the flow field looks like. Is the flame actually distributed, not distributed? Is the colorless, not distributed, or some kind of, and methane as fuel, but we actually use the some of the liquid fuel as the propane fuel, gaseous fuel, which are in the liquid form at the high pressure conditions. And in all cases, the NOx level were pretty low. So that gives the results which you see it here. So you can see the NOx level at even higher equalization conditions of the order of about 1 or 2 ppm, and some cases reaching to about 3 or 4 ppm, and CO emission to be lower too. And of course you can extend the lean limit if you had the pilot flame to about 0.3 or even less than that. You can achieve it in many cases. So here's the soul combustor. We took the motion. Because the gas turbine combustor is basically a cylindrical chamber, and you can see the motion in tangential entry. And here you see the somehow the movie is not working. I had the movie clip here. Okay, it doesn't want to play. Okay, I just wanted to show that the swirling motion, how that looks like over here. And non-CDC mode, it's actually, you can see the evolution of the flame, and it gradually goes around and sits around the periphery of the combustor. And when you see the distributed flame, the flame is actually going very closely when you watch, and you can see the flame, but visibly you could not see any flame in the cross-sectional view of the combustor here. So these are the NOx level, emission level, further tuning it. And now you see the even more favorable results, that even at a very high equivalence ratio, 0.7, 0.8, you begin to see the NOx level to about less than 1 ppm. In fact, that's the limit where even the NOx analyzer won't be able to show what is what. And the CO level, very, very low, only about few ppm. So very highly and favorable configuration, which one can use for the industrial application, very low NOx levels. So where do we stand in terms of the actual emissions, where the EPA limit, anything less than 250 megawatt is 15 ppm for the NOx level. So you can see the 15 ppm level here, and our combustor going from 5 megawatt all the way to 170 megawatt, not fine tuning it. In every single case, we're able to show without any dilution, without any mixing further downstream, we're able to meet the requirement with no problem at all. On the other hand, if we further go and look at different examples over here, so we can show that the limit you can achieve in some cases as low as 1 ppm, 1 ppm, even at 30 megawatt, or close to 30 megawatt. That was very favorable. So single digit NOx demonstrated, and all design gave NO level for the premix case. And the every design, you can see it, that which we examined, very, very high intensity, less than 9 ppm, and of course CO levels less than 100 ppm. And of course, I'm not showing all the results, but basically what I'm saying is that overall, this is where we are. So in terms of where we are, that's my colorless distributed combustion on the right-hand side, CDC. And these are the commercial engines which are available of SE, Bromberry, ABV, Siemens, General Electric, Westinghouse, and different markers over here. And you can see that the uncontrolled emission of the NOx level are combustor design, different design from the different companies is right over here. So uncontrolled emissions are right over here. On the other hand, if we inject the water, which was one way to reduce the NOx level, and many companies actually use this device to control it, so you can reduce this emission from this level down to this level by injecting water or steam injection. People use the lean premix combustion, so you can see the NOx level from the lean premix combustor to this device here. So given that all the engine companies and compared to ours, we are way, way down compared to what's available today. So we believe that this is a very favorable way of reducing NOx emission. And therefore, I haven't talked much about the CO2 emission, but if anybody is interested in, I can give some of the sample number, not the data, but the sample number where we can get to and how much reduction we are seeing it. And typically we can get about 15-20% CO2 reduction. And there's the CO reduction. You can see that in every case, compared to what's available, we are much lower than state-of-the-art CO emission in every single case here. So I'm going to say a few words about the hydrogen-enriched fuel CDC because the hydrogen is becoming more and more important, and I thought it'll be appropriate to see what that is. And we did the hydrogen enrichment with the different fuels. So it's hydrogen is added to methane in this case, in some cases propane. And you can see that even with the hydrogen addition, I'm seeing 3 or 4 ppm. And if I tune it further, I can go down to about 1 or 2 ppm in every case. And so the CO reduction to about 10 ppm. So that's very favorable. So in terms of using the hydrogen enrichment to distribute combustion, basically hydrogen will enhance the stability. It will give you a high efficiency and high performance and very low emission because the hydrogen is a very good fuel. And it also gives the fuel flexibility. So I can use the different kind of fuel which are otherwise harder to burn. And we use the same combustor, lab scale combustor, and here's the example, what we see it here. And I won't show all the data, but it's solar, what you see it here. So in this case, our goal is to have achieved the distributed combustion. So we see the normal flame here and normal combustion flame. So you can see very sharp gradients in intensity, luminosity, and the scale. You see orbital scale on the right-hand side, and that's the boundary of the flame envelope. And as you approach toward the distributed combustion, you can see the entire volume of the flame is filled up at this condition here. And if you look at the RMS values of fluctuation, it's actually going down as you approach to the CDC. So CDC, root mean square values of the fluctuation is actually decreasing. So very, very important in terms of the colorless distribution of combustion. So here's the conventional flame, here's the distributed flame. And so you can see that the vortex which are formed over here, that's the one which contributes to instability, whereas the stable uniform, we see the absence of these boundaries over here. So you can see the large big bang, which you see it on the left-hand side, on the right-hand side, pretty much distributed on the right side. So here the total structure, which you see here with the different hydrogen enrichment going from pure hydrocarbon fuel all the way to about 40% hydrogen enrichment. And on the right-hand side, you see the flame visualization, how that occurs. For flame in a thermal intensity of 5 megawatt to about 7 megawatt and very uniform. And you can see the CDC flame speed and normal swirl flame, which you see at 40%. So you can see the distribution. And on the right-hand side is see the effect of how much the flame temperature effect is. So in the CDC, we actually preheat the air rather than room temperature all the way to 73 degrees, 300 degrees C air preheat. So you can see the adiabatic flame temperature to go up, which is as we expect, but at the same time, the NOx level doesn't go up. And we did a little bit more of the proper orthogonal decomposition for one sample case of 10% hydrogen enrichment for the 5 megawatt. And you can see that the distribution and the peak, which you see it, is actually disappearing. In the normal flame, we see it. In the CDC, we actually dissipating. So these are the different modes which you see. And so zero mode and time constant with the values. And so we see the disappearance of the various cases. And again, for this previous one was for the 5 megawatt, and same thing for the 7 megawatt, pretty much the same features here. In other words, this is more going towards how do we actually apply this to machine learning and the artificial intelligence, and this is where we're heading to, and looking at the same pictures over here. So this actually gives us a means to how do we alleviate these oscillation frequency, and what's the mechanism which is occurring. So in the CDC case, you don't see any of this peak, which you see it otherwise in the normal swirl combustion, and they disappear. More in the same case, basically the CDC, you don't see any peak, and in the other case, as well, combustion, we see the peak at 172, 174, 40% hydrogen enrichment. That's the last example, which I'm going to show, pretty much the same example. That you see the peak frequency showing up at a discrete wavelength, 180, and these are the mode which goes the example here. Basically, they've shrunk down to much lower values when you see these disappearance, and that's more favorable to what you see. So the emission reduction characteristics, you can see the CO emission and normal case over here, and the distributed combustion, very low emission. And of course, CO2 emission is also reduced. And we actually calculated some of the CO2, how much you see it. So you can see a significant reduction in the case of distributed combustion, even with the hydrogen enrichment going from no hydrogen enrichment to 40% hydrogen enrichment. This is a large amount of CO2 reduction, calculated value, which you see it from these examples here. So much of this, you'll see it in one of our book, actually the only book which is available on the topic, so-called the high temperature combustion, that was written by former Professor Tsuji from Japan, myself, and some of the other Japanese colleagues, because I was involved heavily with the Japanese project. And you can see the wide application of the CDC, not for the industrial furnaces. They have the heating application and gas turbine. I showed you some of the example, which we're doing it right now. And the heating application that go over here. And you can actually take care of much of the thermal reduction using different kind of waste, chemical waste, woody waste, hospital waste, municipal solid waste, and all kind of things. You can take care of the high-tech technologies over here. And this is probably the last example. I'll show you some of the reforming, which actually one of the major company in Japan has used this technology and is continuing to use this for producing hydrogen from hydrocarbon fuel, in which case you get the exit gases and you separate out the CO from the hydrogen to get the clean hydrogen. So the normal conventional burner and the high-tech burner, which is the flameless, which on the no color. And so these are, where do we go next? We are actually using this for microturbine, portable power generation, microcell combustion, which is more in the aircraft application, thrust vector control, vehicle going there. And of course, fuel reforming is an important one. And acid gas removal from the H2S, which is the H2S is the important one for the natural gas phase extract. And we're doing some of this to produce a biofuel, liquid fuel. and the other application. So I think, and these are some of the development, which is the microcombustor thrust vector control. And you can see the simple thrust vector that actually steers the vehicle the way you want to go. Very, very useful application, more for the not military application. So this is just the last example, but shown in this picture here, in which the high temperature steam gasification technology, wherein we take a different kind of waste, we introduced it here, and we take a syngas, which is used for power and home heating application, using any kind of waste which is over here in the overall scheme here. So finally, to conclude, we demonstrated basically near zero. I call it near zero because 1 ppm is almost like a zero. And in some cases, even was 0.8, 0.7 ppm from thermal intensities all the way up to 200 megawatt, and CO emission very, very low. And we produce the hydrogen from the methane and the other hydrocarbon, which I haven't shown here, but you can actually use the high-tech technology to produce hydrogen. And we demonstrated ultra low emission. Didn't show the result for the ethanol, JP8, kerosene, but it's exactly the same, which brings us the fuel flexibility and and decrease in oxidation every single case. And of course, the sulfur recovery, which I showed in a couple of examples before, that's the Klaus process, and that's the important one. So that's actually very important. And so it's used for the CDC and the power and propulsion application. So with this, I'll thank you and open the floor for any question or comment. You don't have to ask the question right away. If you have any burning question, you can ask now, or you can send it via email. I'll be more than happy to support the answer.
Yeah, thank you very much, Professor Gupta. Actually, we have two questions here. Can I just read through?
Yeah.
We have only about another 10 to 11 minutes left. So the first question actually comes from Ruban Nanda Kumar. Well, the questions, how does high intensity combustion contribute to the oven efficiency and performance of industrial processes? So that's
I'm sorry, how does the high tech what?
How does high intensity combustion contribute to the overall efficiency and performance of industrial processes?
Yeah, so very good question, first of all. So the theme is really to reduce the emission and enhance the performance. So in most cases, I showed you a sample example of CO2 reduction. That's very important. And I can actually even share what the worldwide application of high tech, how much it's reduced to. It's a tremendous amount of CO2 reduction, which is what we're really after. And the fact that it doesn't give any carbon emission, particulate emission, soot emission, as well as the ultra low emission. So that's really is the key part here. And the second part is to do with the performance improvement, and the fact that it's very uniform. What that means is that overall, it's going to give you better performance. I didn't go into much of the detail, but if somebody is interested, I can share some of the information. Unfortunately, the time is not enough to share that slides and so on. But it actually does contribute to the enhanced performance. And we've shown the performance improvement as much as several tens of percent in most cases.
Maybe Ruben can directly contact Professor
Yeah.
Gupta.
So reduce pollution, including CO2, low noise, low instability, as well as the better performance in the sense that I'm not using as much fuel as I need to do in the other normal hydrocarbon fuel.
Well, the next question, Professor Gupta, how scalable are CDC systems for different industries, and what are the potential environmental impact if they were widely adopted across various sectors?
Yeah, yeah. So that's that's the basically the difference. Which, as I showed you, it's not simply you can take the thing and let me apply it to my furnace. It's I think we need to look at more detail as to how do we translate this to you may have a furnace, you want to apply it here. I showed you a sample example, and the role of fuel air preparation is very critical. So the sample example actually showed you how the fuel air preparation gives you and what direction do we need to go. So I think in terms of the scaling up, again, scaling parameters, if you look at the overall scaling parameters, if you look at the uh, original paper published by Brian Spalding, Professor Spalding from Imperial College, we have something like 120 parameters for the industrial application. So I only showed maybe half a dozen parameter, which it can, how does that vary with the very few parameters which you need to do. So depending on what the industrial application you have, we down select what the parameters are more critical for the given application, and then examine that in more in detail. But what I showed here is that you can take different kind of fuels. You can even take the scaling in terms of the small scale to medium scale to even larger scale, how they were correlating from the limited data which we have available in the open literature.
Well, another question, Prof. Gupta. Could you please advise on the type of fuels and its quality that is suitable for use in high-tech system, specifically municipal waste as a fuel in this combustion process?
No, I think that's exactly where the danger comes in. So don't take as the high tech as the solution, international solution for everything. So I think one thing which um, I want to give a caution of. So if you take the municipal solid waste, you cannot directly use the high tech for using it to whatever purpose you want it. Of course, it'll be helpful, but it won't provide the full benefit. So where we come and provide the basic difference is we take the high-tech technology and reform the MSW to synthetic gas of a good and high heating value. So this is where the application comes in.
Okay, our last question from Professor Jamal. How CDC system compare with others in general in terms of marginal abatement cost?
The cost, of course, cost is the important part. High tech is not cheap. It's it does take some money to, as show the example. Now if you have 2 knobs, now you need to worry about 3 knobs or 4 knobs, so the cost will be somewhat higher. But we must pay attention to environmental issues. As I mentioned, that the population is growing, fuel consumption is growing. If I can only reduce the fuel consumption and yet satisfy the need of the growing population, that's really the path forward. So I think you can see the example from a day-to-day example of what you encounter in our daily life, where cars with the 4 wheels, one car offers one value and the second car offers a second value. One car is only $10,000, the other car maybe $100,000. Both are cars, right? The features are much different. So you can't compare with the normal one, day-to-day operation. It is more, and depending on how much you are willing to go and how far you're willing to go, I think provide the corresponding benefit. But as a society, what we must pay attention to is the undue concern and the rather due concern on the environmental pollution and reducing the fuel consumption. In most cases, we've shown our fuel consumption, energy saving, which is tremendous. I didn't show the detailed results, but I had the data from the industrial furnaces, right? It's not just my data, industrial furnaces, folks who are using it in different sectors worldwide. Something in the order of about 20 to 30% energy saving. In worst case, 10%. 10% is millions of dollars. for the industrial application. So that's where the benefit comes in, right? So somebody asked the question, performance benefit. That's what I'm talking about here.
I think it's good enough already. Question tonight is quite late already in Malaysia. Once again, we'd like to thank Professor Ashwani Gupta for very informative and knowledgeable information and sharing with us tonight. And once again, thank you so much. Maybe Professor Jamal, you want to say something before we leave?
Professor Jamal is a little tired because it's almost midnight, right?
Yeah, we are actually unwinding. It's time for that. Anyway, I must say that as an economist myself, I learn a lot. I gain new perspective when we deal with renewable energy, when we talk about moving forward towards a low carbon economy. So I can see that this combustion technology is still relevant. So thank you so much, Professor Gupta, for entertaining us, for enlightening us. Yeah, it has been a very productive session. Yeah, I think I must say that. Yeah.
Professor Dato' Ali Hassan, last
Yeah.
word from
Thank you very much, Professor Gupta, for sharing with us. Your from your perspectives, very good for us to share to hear your sharing session. Thank you very much. Hope to see you soon physically.
Yeah.
Yeah.
Okay,
Thank you so much, everyone. Thank you so
everyone.
much, everybody, and I appreciate
back-
your putting up with the late in the evening, and have a productive evening, rest of the evening, whatever the time is there before you go to sleep. Really appreciate it. And Professor Yap for inviting it, Professor Jamal, and of course, and Saga for being an excellent MC, making sure everything is working perfect. Professor Jamal, and so it's a small word. Anything I can do or help in any way and elaborate anything which are presented over here, I'll be more than happy to do it. Yeah. Thank you, everybody. And
Thank you very
good
much
night.
again.
Yeah.
Thank you very
Back
much.
to you, Anne. You want to say last word from the MC?
Yes, as we come to the end of our insightful lecture tonight, I want to extend our deepest gratitude to Professor Dr. Aswani itself for sharing his valuable knowledge and expertise with us. Your presentations on the topic just now has provided us, especially me, with a deeper understanding on this critical area in renewable energy. I do not know that this is the kind of big issue, but yeah, tonight I learned something from you, Prof. So it's a good one. And I would like to thank our moderator too, Prof. Dato' Taufik, and also our special thanks to our Emeritus Professor Jamal and Dato' Muhammad Ali Hassan too for joining us tonight. And for those who participate in the join us via the Zooms or stream live on YouTube, your presence and contributions have made today's events great success. So before we conclude, I would love to capture this moment with group photo. I kindly ask everyone to turn on your cameras so we can take a virtual group photo. So please give us a moment to ensure that everyone is visible on the screen.
Wonderful.
Yeah.
Okay, right. Bit more. Okay, we're ready. Okay, Madam Farha.
Right. 1, 2, 3. 1, 2, 3. All right, great. Thank you.
Thank
Okay.
you.
Thank you.
Once
you.
again,
Thank you, everyone.
being
Thank you.
part of
Thank you.
APM.
Thank
Have
you.
a good
Thank
day,
you.
Prof. Gupta.
Thank you, everyone.
Thank you. Take care.
Thank you.
Bye-bye.
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 Thank
Bye-bye.
you. Please stay safe and healthy.
Yeah, you too. Everybody stay safe and healthy. Bye-bye.
Yeah. Look
Bye.
forward to see you in next event.
Yeah,
Thank you,
bye-bye.
Prof. Jamal. Thank you, Prof. Taufik. Thank you, Anne.
Thank you all. Thank you.